All right, so we're ready to go. Yeah, so this is basically his research web. It shows that the drone, flying the drone, but I want to show you some quick videos. Very interesting video using this one. Okay, so this is a good example showing how computer vision can analyze. This is not open. Video demos. Here it is. So this is actually how we use image processing to analyze the unsafe behaviors. You see all the green boxes, so that basically recognize the objects as human being, and then recognize if they follow the safety instruction, especially wearing the hard hat. And if they are following the safety procedures, the boxes will be green.
So the program just detects like the worker's place, so they are in the safe zone, or it can detect like what they are doing.
So for this research, that's the limitation of machine learning. You do need to see that red box. Basically detects if this person was not wearing the hard hat. So this is a limitation of a machine learning model. Usually they can only help you with a very specific purpose. So for this purpose, they only send the training data of wearing hard hat or not wearing hard hat. So the only function this machine learning model can do is to detect if a person was wearing the hard hat or not. But if you can send more training data of the human body gesture, then yes, the machine learning model can also tell you what they are doing. I think his website also includes, so I think you guys get the point, and basically it shows more unsafe behaviors. I think his website actually includes some activity detection as well, but I wouldn't go over that. But so you get the sense. So that is the current literature that we use this imagery data. Vibration, this is something like we give people some IMU. You guys know IMU, initial measure units. So basically you can tell the movement of this person, and then based on that, we can basically infer what this person is working on. And of course, we can track the major equipments like the dosers, cranes, that their current status, idle or active. And people are also using the smartphone mounted to the major construction equipment and to tell their status. So all amazing research, but what is the problem, guys? So if we can do this and this, what can still be the problem? Number one problem we discovered is the privacy concerns. Recall that when I showed you the video from this group, people keep staring at the camera. So they know somebody is monitoring them, and a lot of people are actually not comfortable with that. So that's actually the privacy concern. And number two is the fidelity of your tracking. So here I basically compared, my research team compared the different ways of doing this. So for example, when you use this vibration data, IMU or accelerometer mounted to this construction worker, or the steps camera to check the gesture, we can definitely tell this worker is kneeling down and maybe doing something. But from here, can you tell what this person was working on? Very difficult, right? So based on literature we found, there's another source of data that we have always missed, which is the small tools, the power tools or hand tools like drills, power drills or chainsaws, right? And using this as an example, we collect the vibration data from this power drill, and we applied something called a spectral analysis. The spectral analysis is more kind of like the fingerprint of the vibration. And based on that, we can tell this person is drilling something, but I also can tell the materials, the work interface that he was on. Like he was drilling wood, because the fingerprint from drilling steel to drilling wood will be very different. So actually, just by checking the status of the small tools, we could tell more information from the data. So that's what we proposed. And by the way, any of you knows what spectral analysis is? Anybody? No? So spectral analysis, the raw data, if you're collecting the vibration of something, the raw data is called time domain data. So X is what? Is time, like seconds, right? And Y is actually the vibration magnitude. That makes sense, right? And then the spectral analysis actually we convert that into from time domain to frequency domain. Have you heard about the Fourier transformation? Okay, I think we can cover something useful today. And this is quite important for you guys in terms of research. Fourier transformation, spectrum analysis. I wish I could have a blackboard and show you things. Here it is. Let me see if I can find a good example. FFT. Ah, it's so tricky. So let me see. Oh, I want to find you a good visualization of that. This is not good. Spectral analysis. Oh my goodness! Every time when you try to find something, just disappear. Hopefully, this is a useful example. All right, I think this is a good one. Can you see this graph? So this one shows that for any random waves, you can imagine it's actually a linear combination of different regular waves. Make sense? So if you, let's say, use 0.2 of this regular wave plus 0.15 of this regular wave plus 0.5 of this regular wave, then if you combine them together, you can produce any kind of random waves. So the Fourier or spectral analysis, Fourier transformation, is a way to decompose this raw vibration into the regular waves and give you the linear combination. Make sense? And then the result is something called the frequency domain. It shows the power of different frequencies. So for example, if I have this random wave and I run this spectral analysis and the result give me this, it means that out of different frequencies, the strongest frequency is 40 Hertz, 60 Hertz, and then 85 Hertz and 15 Hertz. So it actually shows the strongest cycle in your raw data, in your raw wave. Make sense? And this is actually a very popular way for us to get the feature from raw vibration data and use that to apply some classification analysis. This is called FFT, fast Fourier transformation or spectral analysis. So what we did then is we basically convert that time domain to frequency domain. This is not raw data, but this is frequency domain. And based on the frequency domain, we know what the frequency domain looks like for drilling things, for puncturing things, for cutting things. We also know for drilling steel, for wood or concrete, how they look like. So from there, from the two data, we can infer semantically rich information like the workers drilling wood. So this is the idea. But the problem is, here's the machine learning part. The problem is, it is very difficult to get enough training data for the machine learning model. Machine learning and artificial intelligence, all the methods are big monsters. We call them monsters because they are so greedy in terms of data. You probably often see, the amazing classification or image processing machine learning model that can tell if this is a cat or if this is a dog, right? But behind the scene is researchers have to send like millions of pictures with labeled information to train the models. That's the only way to get a really good machine learning model to make them smart. If you only have like 100 or 1,000 pictures to send to the machine learning model, I guarantee you, they are still stupid. They cannot do anything for you. The problem for the construction application is because of the privacy concerns and because of the business concerns, it's very difficult to collect a lot of high quality data to train the machine learning model, even though the machine learning model itself can be really good. So then there's a new method called transfer learning or self-taught learning. It's a relatively new concept. It basically shows that if I only have the pictures of dogs, I train a machine learning model, I can still tell if the animal is a cat or not, because dogs and the cats are fundamentally similar. They are mammals. So that's a concept called transfer learning. You just basically provide a very small set of training data of cats, and then provide them with a whole lot of data of dogs and tell the machine learning model the two animals are very similar. You know, they are probably very, very, very small areas can be very different, but in general, they're very similar. So I'm just going to give you the two training sets. Of course, I know the one that I'm supposed to give you is very small. Can you still learn something from there? Fortunately, the machine learning model can do it. That's called transfer learning or self-taught learning, proposed by Andrew Ng. Andrew Ng is actually one of the major players, one of the biggest names in deep learning literature. So we actually propose this transfer learning. So we are proposing is to collect the vibration data from all kinds of vibrations in the world, such like the car vibration, the vehicle vibration, because fundamentally we all live on Earth. And so the vibration data should contain similar features because we are all affected by the gravity and also the material behaviors on Earth. So because of that, we could successfully predict what's going on with that small hand tools based on very limited training data. And the next problem is, and this is what we further proposed here. We also build this kind of telecommunication system. So it's kind of like people are using different tools, but they are also moving so frequently on the job site. So we basically build something called an M node that is kind of like a central hub of collecting data. And we also have the sensors mounted to the hand tools. And so this is the T node. They are moving, but when they move to the coverage of another M mode, the data will be sent to another M mode. It's very similar to the cellular phone, how we use that, okay? And then we have this network of tools. Then we apply something called a spatial temporal analysis. Spatial temporal analysis means we have a network. This is their spatial relationship. So for example, here 1 through 8 shows different tools. And we know for different activities like cutting the pipe, bend the pipe, line up the pipe, and welding, different tools would be used together. So they form some kind of a network. But this network is changing over time. That's the temporal part. So by analyzing how network is changing over time, that method is called a spatial temporal analysis. So we basically analyze how the matrix is doing. Now we actually get a secondary confirmation of what's going on. That's how we basically how we convert or translate the two vibration data into the activities like cutting pipe, bending pipe. So we will have that information. And based on that, we know what's going on. So we basically can, send the right information to the right person. We can send robots, we can send the drones or ground robots to give a warning to the unsafe behaviors, and also can deliver the needed materials and everything to the right place. So this is the concept of what we propose. What do we call it? The Internet of Tools, like a tool network to tell what's going on the construction job site, and also to infer what's going on in terms of safety and productivity. Any question for this research? I'm just giving you an example that how CPS can be useful, but also can be challenging for construction. Any questions, comments?
So Dr. Du, can we use this technology, the vibration, to detect like different type of materials? Like, let's say, the thing I understood here, we can detect like okay, if this worker like drilling on concrete or something like this, but can like this machine tell us this is like concrete or this is wood without doing any activities on it?
Yes. Remember I showed you guys a video last time, a TEDx talk I gave several years ago,
Yeah.
that we used the vibration of the bridge to tell the rigidity of the bridge and how health the bridge is. That is something we actually use the vibration to infer the material properties or structural properties of the structure. So what do you call that? The first order derivative, second order derivative. We can use those derivatives to infer different properties like rigidity and I forgot that, like different things you can input into your computational model. So that is totally doable. Think about that. We also have a lot of other interesting applications. So I'm just going to show you a paper we published, I think last year, that we actually used the vibration to check the pavement performance. If you guys recall, vibration of what to check the pavement? Can anybody tell me? So let me show you this.
Vibration of the cars?
Yes. So basically, we mounted this smartphone on the windshield, and we collected the vibration of the cars. And meanwhile, we use this HD camera to collect the view of that. The reason we are doing that is this is the training data collection. So for any machine learning, guys, in general, machine learning methods have two categories of approach. One is called supervised learning. One is called unsupervised learning. So the supervised learning means you tell them the right answer. So it's kind of like you are teaching the elementary school students the addition. And you tell them 2 plus 3 shall equals to 5. So keep telling them this. And next time when they see 2 plus 3 or 3 plus 2, they know, okay, I learned this before, I know what's going on. Or very likely you only teach them 2 plus 3 equals to 5, and you show them 20 plus 30. Somehow they can infer that it equals to 50, but the fundamental principles you taught them already. Makes sense? That's called supervised learning. The unsupervised learning is I don't teach them anything, but I just throw them a whole bunch of data, and they have to observe what's going on. They have to do mine, what do we call the pattern mining. They have to mine the patterns from the data and somehow group the data, cluster data, find the commonality among the same group and infer something. So most of the machine learning today, you know today, is actually supervised learning, which means you have to provide labeled data. And that's why it's not easy. It's expensive to train machine learning model because we human beings have to manually label a lot of the data to train the machine learning model. Like actually, I know in certain countries, in China and India, it's a job. Like they show you a human face, and your job is to basically plot the area of the eyes, nose, and also the boundary of the face and everything manually using a mouse on the screen. And they pay you, I think 10 cents for each of the picture. So basically hire a lot of people to do it, and they just keep accumulating more and more data. That's why today the facial recognition is so smart. It can also tell your emotion. It's all because of the hard work behind the scene, like people label data. That's called a supervised learning. So same thing for here. We want to tell the road condition from the vibration of the cars, but we do need the supervised learning. So we need to collect the ground truths of the car, right? So that's why we use the camera to collect the imagery data, and we basically document the Unix time, and we use the Unix times to link it to the vibration data. So we know for this kind of vibration, that means this kind of damage. And then we basically run, this is the raw vibration, and that's the time domain, right? So now this is, I think this is good for you to see. This is time domain. So this one basically shows the acceleration, and this one shows second, okay? So from 0 to 1 second, that's time domain. But then we convert that into, hopefully I have a picture of that. Not here, in another presentation. We convert that into frequency domain, and we apply Unfortunately, there's not here. So we apply them in different machine learning model. We will cover several basic machine learning model. And there's also a step called a feature extraction. What is a feature extraction, guys? Can we send the raw data into some kind of a magical machine learning model, and the model will tell us, oh, I know this is a pit hole, this is rotting. Can we do that? No. Machine learning model is like any kind of statistical models or mathematical models. They can only eat numbers. Make sense? So if you are having this image, you have to first convert the image into what? Numbers. So we have to use numbers to show the information, or a voice recognition. So you basically collect the information of my voice, but you have to convert that into what? Numbers. So basically convert them into numbers and send the numbers to the machine learning model. And a lot of times for time series data, what is time series data? So X is time, Y is the value, right? You cannot send the raw time series data to it. You have to get the features from the raw data. This is basically the most commonly used features, like the maximum value, minimum value, the mean value, or the peak to peak, the duration, or maybe standard deviation, curtices or skewness, the distribution of that. And you send those features to the machine learning model. That's how they can make a prediction. Can any of you guess why we cannot send the raw data on only the features? This is about the dimensionality reduction. We will cover that soon, but let me show you quickly what's going on. If we are giving, if I give you a picture, like a picture of Einstein and a picture of Dr. Eric Du, and I want you to tell if this is Einstein or Dr. Eric Du, what is the raw data look like? It's actually the value of each pixel. Make sense, guys? But how many pixels for 1K image? It's very common to have a 1K. Now we are talking of 5K, 4K pictures. So for 1K, that's how many pixels? More than 1 million pixels, right? So now think about that. If a machine learning model has to compare each of the 1 million pixels to see how that is different between Eric and Einstein, that is a lot of work to do. That is actually a really high dimensional data problem, right? So which means you have to use a lot of training data, means a lot of Eric's pictures and a lot of Einstein pictures to train the machine learning model, because every time the machine learning model is comparing each pixel. So what is smarter way? The general features. For example, the color of the hair, the size of the face, right? So if you just use those small subset of features and to teach machine learning model, every time you see the gray hair, that's very likely Einstein. Okay, every time you see the black hair, that's very likely Eric. If we are just comparing Einstein over Eric, right? So the feature extraction is actually to simplify the problem for machine learning model to learn. That's why it's actually a necessary step for that. So we apply that, we try different things, and then finally we could predict what's going on, the damage. The accuracy is not very good, I can tell you. For cracks, it's only about 0.6 accuracy because of the lack of data. Once again, the lack of data is actually a huge problem for machine learning model. And that's actually why today people are talking about big data, because that's the ultimate cue for a lot of prediction models we are having. So I just talk a little bit about like how the CPI system, or in general, the sensing plus data analytics can help with common civil engineering problems, such as structural monitoring, construction productivity monitoring, payment quality monitoring. So I hope this can give you guys a sense. Okay, so any question now? Any question, comments? Everybody's good? We don't have a lot of people today. All right, so last time we talked about the CPIs, but we basically skipped the fundamental the fundamentals about data science or information science. So that's what we want to do today. So let me share my screen. Oh, sorry. Should be green. Here. All right. Can anybody tell me the terms, the words you see on the screen, are they the same or different? Data, information, knowledge, and wisdom. Are they the same thing or are they different thing? They are different things, right? Okay, let me give you a quick example. I know, if I say if data and knowledge, if they are the same thing or not, most people would say, no, they are different things. But a lot of people still believe data and information are the same thing, and they tend to use data and information interchangeably. For example, I don't want to give you my personal data. I don't want to give you my personal information. You would think that's the same thing, right? But let me show you, we need to be very clear about their definition. What's this? This some soundtrack, right? Let me play this one. Oh, you cannot hear anything. Anyway, so this one is playing a song, the engine light is on. And this one is playing this soundtrack. Make sense? And what's this? Now, by hearing this one, the engine light is on, you are thinking something's wrong with the engine, right? And finally, based on experience, I probably need to add oil. I need to change oil, right? So this is a quick example showing 4 different things. This fundamental thing is called data. They are symbols. There's no meaning. By staring at this thing, you cannot tell what's going on. You don't know the meaning. Meaning means something that can trigger a chain reaction in our brain so we can think. But just by looking at this soundtrack, we cannot think anything, right? So that's called the data. It's actually the way that the machine exchange the raw information, the raw data. But based on that, we have the translator. So for example, operation systems can translate your soundtrack into a song. And by listening to the song, we know, oh, we understand the meaning of the raw data. We comprehend the meaning of raw data. When there's a meaning, when your brain starts to sync it, we call this information. We don't call this data anymore. Make sense? So the biggest difference between information and the data is actually information has a meaning. Knowledge is a higher level of that. So if you show this, the engine light is on to a child, to a kid, they probably wouldn't understand what that means, right? Yes, they understand each word here. They understand the engine light is on, this event, but what's behind this event, what it means to my car, they don't understand that. And if you understand that from the information, that is called knowledge. You know that. But the highest level is called wisdom. It's called informed decision. So this is something that you can predict. So even though you understand something's wrong with the engine, but you cannot still predict the future behaviors of that. You cannot predict what you should do to mitigate that. But when you are able to predict that, which means you have the wisdom, that's informed decisions. So those are the building blocks of information system: data, information, knowledge, and wisdom. So the entire purpose of the foundational building system is actually to move from the lower level to the higher level. Make sense? How we can translate the data to information, to inform the knowledge, and finally to predict something. That's the wisdom. That's the information system. So this is the hierarchical model of wisdom. The fundamental level is data, is discrete elements. It's used to describe the system, the status, the system, using the words, numbers, codes, or like the soundtrack, right? The raw data. And when there's a system like a person or some computer program or operation system to interpret the description, the raw data, and the result is actually the information. So the information is something that people can understand, now that people can comprehend. There's a meaning. So we call it a linked element. So when you link the words and numbers together, when you see an Excel spreadsheet with all the numbers, so now you can infer the productivity, the profit of this company, the cash flow of this company, and you can basically infer, oh, it means we are earning profit. So then that start to have this information. And higher level is organize the information, that's called understand. So if you see this spreadsheet with good profit for this department and not good profit for that department, but a much, much better profit for the third department, and if you put everything together, and if you are trained accountant, and you probably know my company is in good shape. That is the overall comprehension of what's going on. That's called understanding or knowledge. And finally, based on the continuous learning from the past data, you can make a prediction and take actions. That's called a decision or applied knowledge. So the information system is actually doing the four things. For data, we care about how we can better collect data. So we use the sensors, we use the cameras. That's all about how we can collect the raw data. And from data to information, that's the process called mapping. So I have all the imagery data, but I want to translate that into human activities or varying or not varying hard hat. And that's the quick fact from the collected raw data. And that process or that machine learning process, guys, is called mapping. And now based on, how many people were not varying the hard hat, I can tell if the job site is safe or not. That's called the learning. And once again, from mapping to learning, people tend to use a lot of machine learning algorithms today. And finally, the forecasting is about what actions I should take. And so there's something called heuristics or logistics or logic reasoning. Like, if I do this, then what would happen? So you have to teach the model a lot of things. Or sometimes if this is not an automated system, and this is more about like a person takes action based on our information. And this is another visualization of the wisdom of different levels of information. So data, they are basically unconnected, isolated piecemeal of elements. And when we connect them, that's called information. And when we connect information, that's called knowledge. And finally, when we have enough knowledge, when we have enough past experience, we can make prediction, take actions. That's called wisdom. Okay, so maybe this is very conceptual, very abstract, but let me give you another example. What do you see? Can anybody tell me what you are seeing that? What are you looking at right now? It's a matrix, and it's okay you don't know what you are looking at because this is data. Make sense? It's just the raw numbers. Now you know what you're looking at, right? Because if I color code the numbers, if the number is smaller, I give it a darker color. If the number is bigger, I give it a light color. Actually, this is called a grayscale. 255 is black and 0 is white. So it's all from white to black. And once I do it, now you start to see this human face. So this is data, this is what? This is information because you know what they're saying. There's a meaning. And can anybody not tell me who he is? Who are he or she?
Abraham Lincoln.
Exactly. That's what? That's knowledge. Now it basically, it's not only about you, it's not about you comprehend the raw data now. It's also about the further information about that. So that's Abraham Lincoln. So that's basically data, information, knowledge. So what is wisdom, guys? Yeah, Abraham Lincoln. Wisdom is this. By the way, there's this is actually what I found online. It's very interesting too. You can just get any picture, upload a picture there. They basically will convert that into a grayscale picture and convert that into this matrix. I actually tried to convert my own picture into a matrix. And so next time you can send this to a friend and ask them to guess what that is. You know, this is a way to, okay, I think here it is. And we'll talk about wisdom later. So data, this is the definition. Data is symbolic representations of facts. So they are symbolic, which means we don't see the meaning. Only machine uses it as an instrument to exchange information. Data can be language, mathematical, or other symbolic representations, which are generally agreed upon to represent people, objects, events, and concepts. So for example, in this case, the only way that if I open this matrix in my computer, it shows the face of Abraham Lincoln. You open it in your personal computer, it shows the same Abraham Lincoln, because we actually have agreement that 0 is black and 255 is white. So we have to stick to the same rule. Example is actually grayscale matrix of picture. Information, that's interpreted data. So information is the result of mapping. Think about that. What is mapping in our case? I basically find this color, I check what kind of a gray color I should give to 204, and I give this color. This process is called mapping. Make sense? So information is the result of mapping, formatting, organizing, or converting data in a way that increases the level of knowledge for its recipient. Therefore, information is produced from data. So data are viewed as being objective by nature. But information is subjective and exists only relevant to a recipient, okay? The nature and the significance of any information is primarily a function of the attitude, situation, and relevant responsibility of the people involved with it, which means what? So what I see a human face, maybe it's not perceived as a human face by another person, totally affected by, you know, how you comprehend that. Whether the need is to provide accountability, a statement of problem, or parameters for decision process, a clear representation situation is a major function of information. So we just give you the representation of the raw data. And in our case, in our example, the information is the image showing a shape, and we know the shape is a human face. Knowledge is actually to be well informed or level of understanding of an area. So it's used to describe the understanding of the reality. So in here, we know this human face, and because we learned history, we have seen Abraham Lincoln before, we know the name for it. But think about that. My raw data, 0 to 250, doesn't contain any information about Abraham Lincoln. None of the letters. You know that because you trigger some memory in your brain, and you basically link it to the information you have. And this is the knowledge process, okay? So knowledge is knowing what's happening. For example, in our case, the shape in that image is Abraham Lincoln. What is wisdom? Actually, there's a very interesting case. Actually, somebody, I forgot the name of the person, cardiologist, oh here, cardiologist John Sotos, based on the picture of Abraham Lincoln, he diagnoses that Abraham Lincoln actually had a disease called MEN2B, a genetic disease that causes aggressive thyroid cancer because of the hood eyes, asymmetric jaws, and this and that. This is wisdom. Why? We couldn't tell this from his picture, but he could. He could do what? He could predict the health condition of Abraham Lincoln. And this is basically that doctor should have a lot of knowledge from different patients. He accumulated a lot of models himself. And that's the only way that he links all the knowledge together to make a prediction for a particular case. That's the highest level for any information system called wisdom. Make sense? So wisdom is the overall level of judgment developed based on the knowledge accumulated in one area. So wisdom is knowing what path to take next, the ability to predict, okay? Now, for example, in this case, I could recognize that it was Abraham Lincoln based on the limited features, but I could not tell this undiscovered disease because I didn't have the wisdom of that. So we also talk about this several physical system. Now you see the similarity between the model of several physical system and the model of information system, right? The fundamental level is always often about data. the medium level, the middle level is always about information and knowledge, and the highest level is always about decision making. That's interesting, right? So it means the developer of this several physical system or the standard of several physical system actually referred to the standard of any information system, from the fundamental level of data sensing to the medium level of understanding the situation, knowing the situation, that's the information knowledge, and all the way to the knowledge level. Okay, so now since we know the basics, what's going on with the information system and information technology? Those two terms are, once again, often used interchangeably by different people. So definition, information system is actually, let's say, information technologies. So information technology are computer technologies and telecommunication systems that help the acquisition, processing, storage, and dissemination of all types of information. So think about that. It's the hardware infrastructure for that information system model, like from how we should collect data and how we store, where we store the data, and how do we do the mapping faster, the algorithms to do the mapping, for example. That's all about information technologies. One thing is the computer, one thing is the telecommunication system, store, analyze, and exchange. But the information system is much more than that. It's about people, activities, ideas, and machine. So we can say information technologies is part of the information system, but that information system, let me show you here. This is the information system. So information system actually includes three things: information technology, people, and a process related to that. So the technology can include the hardware, software, the database, the networks to connect all the data, and other related hardware components. They are used to build the information system to support different functions. But the main thing is the user of the information system is the people, and the policy procedures, the standard, for example, the SOPs, standard operation procedures related to that. The entire thing is called the information system. So the quick question is, do we have information system or information technology for a long time? The answer is, since the very beginning of a human civilization, we had information system all the time. We just started to have information technology. Let me show you this. This is actually the Jiesheng discovery in China, and also the Quinpu discovery Inca. And you guys know what they are, what these are? These were the flash drives in ancient time. These were how people document and record information. They basically use these threads, and the nodes on the threads to document the numbers and document events. So those are the ancient Chinese characters. I can recognize something like this means son, this means grandson, this means happy. I don't know what this. This means lunchtime, and this means big, and this means sky. They basically use the shape on the nodes of the shape of the nodes to document things. And that means 10, 20, 30, 50, 60, 100, 1,000, 10,000. I don't know why it is, but this is 130. So this is how they document number. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the flash drive at that time. And similarly, think about that's interesting. Or about the same time, on the different sides of the earth, people were using exactly the same methods to document numbers and words. So this is actually Inca, Quinpu, and they follow different standards, but they were using similar way to document information. That's the information system, right? That's about the process, how people use that, how people store it. It's not information technology. Or maybe we could call it information technology from 5,000 years ago. Oh no, 7,000 years ago. And you guys saw this before? Abacus, it was once again, ancient China about 5,000 years ago calculator. So they just use, I remember when I was a kid, I was forced to learn how to use this, guys. And if you learn how to use this, it is much faster than calculator. I don't know why, but it is much faster than that. So basically here, all the numbers here means the what do you call that? Not the individuals, like 1, 2, 3, 4, 5, and all here that means the tens. So that's a 10, that's 20. So just by moving those those, I don't know, call them those bins, and then you basically show the number, and this small device, this small instrument can do all the arithmetic calculation, addition, multiplication, division, in very fast speed. And this is a picture from about 1,000 years ago in Europe. You see this picture, calculating table? That's also very interesting. Like people from different areas of Earth, they were using very similar approach to do this. This is the data analytics. And this is how we map the raw data into information. This is the information system, once again. And this is the pigeon post. That's 180. And what's that, guys? This is internet at that time, right? Once again, information system, information exchange, it's just we didn't have the technology at the time. So think about this. We have been moving over 5,000 to 7,000 years period of time. We have been moving from this to this data center. We have been moving from this Abacus to this high performance computing center. And I've been moving from this pigeon network to more like an internet or data exchange network. To me, they are still the same thing. They still serve the same functions, right? Storage of data, data analytics, and exchange of data. It just, we can make things much faster. So are they information systems? Yes. Are they information technologies? By the definition of today, those things were not technologies, but those things were technologies. That's how we define information system and information technologies. Make sense? Okay, so let's take a 15-minute break and let's return at 5:25. Okay, see you guys then.